For now, though, we're going to wrap up our talks today with our last speaker. I am pleased to introduce Emilie Purvine, who is going to talk to us about the homology of graphs and hypergraphs.
All right, thank you. Thanks for the introduction, and thanks to Rick for the invitation. The talks have been fantastic so far, and I'm looking forward to hearing more tomorrow. Thank you guys for sticking out to the last talk of the day. And let me add to my list of thanks all of my collaborators for this work. A number of folks that I've been working with at Pacific Northwest National Laboratory, and then a lot of this work started as a collaboration at a Women in Computational Topology workshop. So a number of those folks I've been collaborating with for the last probably about 5 years. And then we also teamed up with Michael Adamaszek and Henry Adams on some work as well. So this talk is going to be kind of a survey of some work in this graphs and hypergraphs that has been going on for about 5 years. So I'm going to start in Graphland. And in both cases, graphs and hypergraphs, I'm going to start by just reminding everybody about combinatorial structure of these objects. I come from the background of discrete math and combinatorics, not from topology. All the topology I've learned in the last 10 years or less from these amazing colleagues of mine. So I'm very motivated by data and the combinatorial structure, but also what we can learn from the topology as well. So I'll start by talking about graphs, the persistent homology and homotopy type of metric graphs, and then the second half of the talk will be on hypergraphs and different notions of homology for hypergraphs. So let's dive into graphs. As everybody probably knows, but I'll remind you anyways, graphs provide a mathematical model of data that is focused on two-way relationships. So if you've got vertices and edges that connect those vertices pairwise, and you want to ask things about connectivity, large-scale connectivity, clustering, and model these kinds of pairwise relationships. If you only care about who is connected to who pairwise, graph might not be what you need, but if you're looking for things like longer level paths, higher level connectivity, more than just the single pairs of entities, then a graph is for you. So the types of combinatorial things that people, network scientists typically consider are the degree or the number of vertices that are adjacent to each vertex, or the number of edges incident at a vertex, either the degree of a single vertex or the distribution of those degrees. We look at paths or walks, and then diameter being the longest distance within the graph, paths being sequences of adjacent vertices. Connected components can be useful. Of course, this is a single connected component. There are various notions of centrality on vertices that people care about. These are 6 that were on Wikipedia, but there are many more. It seems like every day somebody is coming up with a new notion of graph centrality to measure something or other different than these kind of more historical measures of centrality. And then getting to maybe a little bit more topological properties, clustering coefficient looks at the number of triangles that are incident at a vertex versus the number of possible triangles that one could have. And then triangle counting generally around the graph, and maybe cycle counting is the generalization of triangle counting. And then there are just so many more on and on of things that people care about in the combinatorial structure of graphs. But what I want to talk about more is the topological structure of graphs. So there's a very simple interpretation of topology of a graph, and that is through a one-dimensional simplicial complex. So of course, a graph, if you missing the vertices here, but if you think of a graph as a bunch of vertices or zero-dimensional simplices glued together by one-dimensional simplices, you get a very straightforward simplicial complex. But the topology of that is not terribly interesting beyond one dimension. And so to get more interesting topological structure, we move to a metric space. So a metric graph assigns a positive length to every edge. If you have a simple structure, you might just assign 1 to every edge if you don't have a distance. And then in particular, going beyond that, every point along an edge has a distance proportional to both endpoints of that edge, proportional to the length and how far you are along that edge. So it's no longer a finite space, it's now an infinite space in which every point along an edge is allowed to be a point in your metric space. the natural metric on this metric graph is the infimum of all path lengths between the 2 points. And we're going to denote the metric space by bar of G. One concept that's going to be important in what we talk about next is the loop of a metric graph. So a loop of a metric graph is a continuous map from the circle into the metric graph. We may use the word loop to identify the image of that map. So all of these things that we would consider in the English language being loops are what you would think of as loops, but also the longer loops that are the sums of other loops. The length of a loop is the length of its image in the graph. Okay, so now we have a metric space. And what do we do when we have metric spaces in topological data analysis? We do persistent homology. So let's just remind ourselves kind of the ingredients for persistent homology in this, when we don't have a point cloud, but we have a particular specific metric space. So we consider any subset of our metric graph G, which could be the whole metric graph, or it could be a finite set of points, maybe just the vertices of my metric graph, and a scale parameter R, the Viator-Rips complex for that specific subset X at scale parameter R is the set of finite simplices contained within X whose diameter is less than or equal to R in the metric graph. So even if X is infinite, we only have our finite simplices. So here's an example where our X is just the set of vertices in this metric graph, and we're looking at scale parameter 2. Of course, I haven't drawn all of the simplices, but just giving you an idea, noticing that around these bigger loops, we get a bunch of triangles glued to each other. And in these smaller loops, we get them completely filled in with tetrahedra or tetrahedra glued to triangles. And then a filtration of these Viator-Rips complexes will give you, of course, a homomorphism to associated homology groups, and you can get your persistence diagram from these maps of homology groups from R to R prime, where you're increasing your scale parameter. Okay, so those are the ingredients for our persistent homology of a metric graph. And back in 2017, this is the first result from the Women in Computational Topology group. We were able to show, basically fully characterize the one-dimensional persistent homology of a metric graph. So we have, let's say we have a finite metric graph of genus G, meaning that it has G elementary cycles. And the shortest system of loops are C1 through CG with lengths Li for each of the loops. We order them in increasing order. So if C1 is the smallest loop, CG is the largest loop. And shortest system of loops just means lexicographically shortest. So if you have multiple systems of loops, you can think about one loop and one loop. The sum of those two is also homotopic to one of the two. And so you would want to take the elementary, the smallest loops. So the one-dimensional Viator-Rips persistence diagram of the metric graph here is simply the points 0, Li over 3. And this is what intuitively when we would hope it to be. We can just track all of the loops. But the question we had is, should there be any interference between any of the cycles? Could there be any interference? So of course, this is not news to anybody. The intuition that the cycle is killed at Li over 3. Of course, if we take a cycle and we space 3 points evenly around on it at the scale parameter Li over 3, we get this cycle is filled in. Of course, it completely gets triangulated. Because we're in this this metric graph, it's not just this a bunch of triangles. We have an infinite number, parameterized around that whole cycle. But the whole thing is killed at least at Li over 3. So in this proof, we needed to show two things. First, that the cycles don't die any earlier. And why would they? But maybe there's some interference again between two neighboring cycles that would cause some cycle to die earlier for some reason. And the second is that no other cycles are created, again, due to interference. So we proved this by using a linear algebraic argument. So to prove the first one, we showed that the cycles from Ci all the way up to Cg, Ci plus 1 up to Cg are linearly independent in the range between Li over 3 and Li plus 1 over 3. And then we also show, to show number 2 here, that those cycles span the homology group. So so that means that, you know, none of the cycles is a sum of other ones and nothing else is needed to span. And so then we get the final result. So this is one-dimensional persistent homology of any metric graph, any cycles, structure, any structure that you have. What about higher dimensional cases? I'm going to call back a little bit to Henry Adams' talk yesterday. And this he mentioned, and I think Facundo mentioned this as well in his earlier talk, that they characterized a single cycle of length 1 in all dimensions, at all scale parameters R. And so essentially what this result is saying in the persistent homology world is that the one-dimensional persistent homology has a bar between 0 and 1/3, which is exactly what our result on the prior slide would imply. But then in higher dimensions, in 3 dimensions, there would be a bar between 1/3 and 2/5, and so forth, going up the scale here. And so this is characterizing one cycle in any dimension. And so the next natural question is, what about higher dimensions and more than one cycle? And so the thought that we had, so the Women in Computational Topology group teamed up with Michael and Henry to prove kind of an iterative gluing result. So given that we understand the characterization of a single cycle, let's try to build up the topology of a complicated graph by gluing cycles together. And the hope is that when we glue the cycles together, again, that we won't get interference between neighboring cycles. So we proved conditions upon which that is true. And so that it comes from a more general result that we proved, which is on general metric spaces and gluing together metric spaces, but I'll state it here in the language of metric graphs. So you can see the image here. If I've got 2 cycles or 2 metric graphs generally, whose intersection is some set A, or G sub A is the graph. This A, which we're calling the gluing region, has to have some nice properties. First, it has to be a path, a simple path. Although in one of the graphs or the other, let's say in Y in this case, you can have branching in G sub Y off of A, but you can only have branching off of your path in one of the 2 graphs, GX or GY. The other thing is that it can't be too long. And what does that mean? So if we take all of the loops that pass through A, so on the X side, they pass all the way through A. On the Y side, they may not pass all the way through A because you could have a smaller loop over here. But if you take all of the loops that pass through A and you take the length of the smallest one, alpha has to be, the length of A has to be less than that L over 3. So it has to be small enough so that you don't have like a really small cycle going through that gluing path. So under those conditions, what we wanted to be true is in fact true. So the Vietoris-Rips complex of the union of those 2 X and Y over A at the scale parameter R is homotopy equivalent to the Rips complex of X at scale parameter R together with the Rips complex of Y at scale parameter R, taking those 2 unioning over the Rips complex of A at scale parameter R. And this is true for all scale parameters R. And so if you take that characterization at a single scale parameter and you sweep across all, then we get the result for persistent homology. So if we know the persistent homology for one graph and another graph, and we glue them together along this nice piece, as long as the nice piece is contractible in the Rips complex, then we get the persistent homology. You can just put them together. And so that was the result we got in 2020. So just a little bit about the kinds of graphs we can characterize using this and the kinds that we cannot. I've gotten just a few examples here. The first one we call a bouquet, where we just wedge a bunch of circles at a single point. Not terribly exciting, but still we can characterize this using our result. By characterize, I mean we can come up with the homotopy type or the persistent homology of the full graph by iteratively gluing it together from smaller graphs. This second one we would call a tree of loops. So we take loops and we glue them together along single edges, or we glue edges as well along single vertices. And we don't come back around to each other. So if this edge were glued to this edge, that's not a tree of loops anymore. But these are obviously easy to build up. This third one is getting a little bit more complicated because in the case we can glue these two circles together along a single edge, but now we need to glue this third one on along two edges, which is still fine. The cycle is length 7 and the gluing path is length 2, so that's less than 7/3. But there's branching over here, which is allowed in the theorem. This last one is one we cannot characterize using our result. There's not a way to build this graph up iteratively by gluing circles or loops together that doesn't involve gluing it kind of to itself. So you could take 3 squares as a ladder and then fold it around, but that's self-gluing and that's not allowed in our result. Or you could maybe take 3 a ladder and then glue another cycle onto the face, but that's gluing along kind of 2 paths, and that's also not allowed. And the final way is taking pretty much everything except for this one edge in one graph, and the other graph is the whole 4 cycle. But again, that's a cycle of length 4 glued along a path of length 3, which is also not possible. So really, there's just no way to use our theorem to characterize this last one. The last thing I want to say about this theorem is that order really matters when you want to apply it. So this graph is completely fine. We can totally characterize this one using the result, but only if you do it in the right way. So if you first glue C10 to C9 plus epsilon, remember the prior result had a less than instead of less than or equal to on the length of the gluing path. So you can glue C9 to C9 plus epsilon to C10, no problem. And then you can glue on C3 plus epsilon, also no problem, because the length of that smallest cycle is 3 and the gluing path is 1. So perfect. But if you first glue the 9 plus epsilon to the 3 plus epsilon, you're fine. But you then cannot glue on the C10 because you've got a cycle of length 3 going through a gluing path of length 3. And so that does not satisfy that gluing path being smaller than the smallest cycle over 3. So you just have to be careful about how you iteratively glue these things together. Okay, so before I move on to the homology of hypergraphs, let me just summarize what I've talked about thus far for graphs. So we have this simple interpretation of this one-dimensional simplicial complex, of course, but once we get past just saying that the homology is the cycle structure that we see in the graph, that becomes less exciting. So to get more complex, we build this metric space from the graph, a metric graph in particular. We use the persistent homology of the Vietoris-Rips filtration. And in dimension 1, we have a complete understanding in terms of the shortest cycle basis. In the general case, we can characterize the persistent homology via iterative gluing of graphs, but only if they satisfy these certain restrictions. And of course, it relies on the Adamaszek and Adams result on knowing the homotopy type of a single cycle. But of course, as we saw in the prior slide, some graphs can't be built up this way. Just a brief advertisement for the AATRN Vietoris-Rips seminar that's coming up, I think, this Friday. My colleague Bei Wang is going to be giving a talk with a lot more of the details on those prior theorems that I just described on how we actually proved those. So I'm sure you can click on this, but if you just Google AATRN Vietoris-Rips, you can find the schedule and the link for getting to that if you found this part of the talk interesting. And then since this is a workshop on theory and applications, I just thought I'd mention a couple of things that we think would be useful here. So metric graph structures can be found in a whole lot of different places, maybe transportation graphs, brain functional networks, and I didn't list any other ones here, but there's many places where graphs have geometric embeddings that are useful and the distances are meaningful. Power grid is another one, and perhaps studying the topology of those metric graphs could be useful. And then another application is potentially for scalable computational algorithms. Using this iterative gluing method might allow you to compute the persistent homology of larger metric graphs if you can decompose them. A recent talk I saw by Vidit Nanda talked about an ear decomposition of a strongly connected directed graph. And I'm wondering if maybe some ear decomposition. Of course, if you're just looking for the one-dimensional persistent homology, knowing the generators is enough, then you don't have to do anything more, right? But if you're wanting higher dimensional homology and you can compute a minimal generator basis, then you might be able to take those and kind of just look at how they're assembled. But right now, there's not a way to tell algorithmically whether you can actually do that.
Cool, thank you.
Mm-hmm. All right, so I will move on to the hypergraph section. Okay, so hypergraphs are something that my group here at PNNL has been very interested in lately, mostly from a combinatorial perspective, but we also recognize that there's some rich topology and topological structure that we are also very interested in. So just introduction to hypergraphs. They, just like graphs, they provide a mathematical model of relationships, but now not just pairwise relationships, but groupwise or multi-way relationships. Again, we want to ask questions about connectivity and clustering structure and model these multi-way relationships. This is a co-occurrence of characters in Les Mis. So each hyperedge here is a scene and each vertex is a character. And so we see that there are some characters that are more central to the story and some that are less central. And this might be harder to see if you were to squash this down into a graph, because this here would be a really big clique on a whole bunch of vertices, and it might not be so obvious that this character right here is really central in the middle of the system. So just like in graphs, again, there's combinatorial structure to hypergraphs. Here's an example of a hypergraph that we've cooked up. The degree or degree distribution, of course, you can ask the same question, how many hyperedges is each vertex contained within? But you can also stratify the degree by asking how many hyperedges of size at least 1, size at least 2, 3, 4, and so on, and get a stratified degree distribution. You can also compute edge size distributions, which is something that's very boring in a graph because all edges are size 2, but in a hypergraph, the edges are different sizes and the edge size distribution becomes potentially interesting. There's a notion that our group has come up with called S-connected components, which is built off of S-walks and S-paths, but basically an S-connected component says what set of edges are connected so that between any pair of edges, or for every edge that's in my connected component, it intersects with something else in that component with size at least S. So notice that this blue edge up here only intersects in size 1, and so it's kicked out of the 2 components. Same thing with this green, red, and purple edge down here, they're kicked out. Down here is a 3 component, everything else is splintered off, but this remains as the intersection here is size 4. So an S walk is a sequence of edges so that pairwise they intersect in this sequence at size at least S. So this is a 1 walk here. If I go from 5 to 3 to 1, back to 5, 10, and then 12. A path, a 1 path, is something that doesn't repeat any edge. And so I go from 5 to 10 down to 12. And then there's a 2 path, which requires intersection to be size 2. And now I see that to go from 5 to 12 takes a little bit longer to get there if I require stronger intersections. You can then compute diameter and so forth from the notion of this path. And S-connected component then comes from, I should have probably swapped those two. S-connected components are sets of edges that are pairwise connected by at least an S path. S-centrality then, a lot of centrality in graphs comes from the notion of a distance or a path. So you can stratify, again, the centralities by using S-paths and S-distances. So here is a heat map of edges colored by their 2 between this centrality. Notice that, of course, this central fat core is going to be your high, and then your peripherals are your lows. Quick advertisement, again, for HyperNetX. This is a Python package that's that we've put together here. Lead author is Brenda Pregastis, and she has put together a wonderful library with a number of other folks here at PNL to do all of these things that I've listed here, at least the ones in orange, on hypergraphs, and we're working on scaling that. So if you want to play with hypergraph data, please check out HyperNetX, clone it, and be a contributor if you like. So there's also clustering coefficient and triangle counting kinds of analogs, but they're a lot more difficult to define in a hypergraph than in a graph. Okay, so that's the combinatorial structure. Let's talk a little bit about why we would want to do topological structure. So in a graph, it was very obvious, at least to me, that originally a graph is a one-dimensional simplicial complex. So there's an obvious topology there, and then there's this simple metric space that one could create because graphs are inherently pairwise things and distances are inherently pairwise things. And so it just made a lot of sense to consider the topology of a graph. But what about for a hypergraph? Well, let's step back for a moment. Generally, topology is used to understand the shape of data, holes, flares, things like that, usually done for TDA, at least on point clouds and metric spaces. So for a hypergraph, the analog then would be trying to build topological spaces from hypergraphs or point clouds or metric spaces from a hypergraph, and then going to town with our favorite topological analysis. So there is an obvious one, transformation from a hypergraph to a simplicial complex, which I'll describe on the next slide. But really the goal is to preserve some amount of information about structure, maybe included edges, maybe intersection structure among the edges, but without adding or removing structure to the hypergraph. We don't want to damage anything. In the graph, we didn't have to add anything. The distances were inherent, they're intrinsic distances, or the simplicial complex is literally the same as the graph. And so we didn't add anything at that point. So we want to try to do as little damage to the hypergraph as possible. So let's talk about what we can do. Of course, the simple interpretation I mentioned is the simplicial complex closure of the hyperedge, so for hypergraph. So for each hyperedge, we add all of its sub-edges. So here is a hypergraph. We had all of the three-way sub-edges of this four-way edge. We add all of the pairwise edges. We add all the singletons. We get the super complicated hypergraph, which is just the simplicial complex that's associated. But of course, this goes against what I said on the prior slide about adding information, because we've added a whole bunch of relationships that weren't there in the first place. You can still do it, of course, but you're adding something to the hypergraph. You need to be aware of that. So there might be some other more complex ways of doing it to try to build other simplicial complexes or chain complexes without adding or removing any information from the hypergraph. And I'm going to talk about some of them in this rest of the talk. So 3 of them: restricted barycentric subdivision, relative barycentric subdivision, and embedded homology. And then we'll talk about some other finite topological spaces that you can create. And then the question is, for each one of these topological notions, one might say, what hypergraph properties do each of these topological interpretations capture? What do we see when we do these different transformations? So before diving into the first one, let's step back for a moment, and instead of asking, instead of just coming up with something and asking what it captures, let's ask the reverse question. What is it about a hypergraph that we want to capture using homology? And so one potential answer is that we want to capture the structure of the interactions among the hyperedges. Okay, so there's a well-known construction that's associated to a bunch of sets, of course, called the nerve, which I'm sure most of us understand. So if we have a bunch of, let's say, open sets, here I have a bunch of sets, but let's pretend that they're open sets in some topological space. The nerve complex of that collection of open sets is shown on the right here. So you take each open set turns into a vertex, and then you create a simplex among a set of vertices if and only if the intersection of all the edges is not empty. So the nerve of this hypergraph, or of this collection of open sets, is shown right here. Now, there's a relationship or another hypergraph that's associated to my original hypergraph. It's called its dual, which is formed by swapping the roles of vertices and edges. So this vertex right here corresponds to this hyperedge right here. This hyperedge contains two vertices, and so its corresponding vertex in the dual is going to be contained within the two hyperedges that correspond to those two vertices. So we've just swapped the two notions. This is, if you take the hypergraph and you create its incidence matrix of vertices by hyperedges with a 0 or a 1 if and only if the vertex is contained within that hyperedge, and you take the transpose of that incidence matrix, you get the incidence matrix for its dual. And this is a well-known duality result called the Dowker duality theorem that says that the basically the simplicial complex associated to this hypergraph, stated differently, but the simplicial complex associated to this hypergraph is homotopy equivalent to the simplicial complex associated to the dual hypergraph. And it's not difficult to see that the nerve of a hypergraph is exactly the same as the closure of its dual. And so if these two are homotopy equivalent, that means that the nerves are homotopy equivalent. And that means that if I want to study the intersection structure of all the hyperedges here, all I need is, to get up to homotopy type, is the simplicial complex of that hypergraph. So do we really need anything else, right? Should I stop the talk here? We have it. We don't need any other topological structure associated to the hypergraph. And I would argue that yes, we do need more because this is only one aspect of the hypergraph that we might want to capture. But just know that the closure of the hypergraph, or the simplicial complex of the hypergraph, while adding a lot of information to the hypergraph, actually is related specifically to the intersection structure of all of the hyperedges. That's the point I wanted to get across here. Okay, so let's go and try to come up with some other notions of homology or topological structure for a hypergraph. And just kind of see what else we can capture that's not just the intersection structure. So we're going to start here with the barycentric subdivision, and I call it the restricted barycentric subdivision because we're not going to take the barycentric subdivision of just the simplicial complex associated to the hypergraph. So if I start with a simplicial complex, the barycentric subdivision is formed by replacing each face or simplex with a vertex, and then we connect to all of the subfaces, and then we take the clique complex of the resulting one skeleton. So here's the triangle and the barycentric subdivision of the triangle. So for a hypergraph, of course, we don't have that full structure, and so we can do the following construction. We can form its closure, or its simplicial complex. We can get the barycentric subdivision of that, and then we can restrict that barycentric subdivision to just the vertices that correspond to hyperedges in my original hypergraph. So A, B, and B, C were the only hyperedges here. And so that I'm going to restrict my barycentric subdivision just to those. Now there's a simpler way to get here. This was illustrative, so you can kind of see how we originally thought about it. But the simpler way to build it is to build the partial order of edges by inclusion. And then you take, I believe this works. Now I need to double check, but and take the clique complex of that partial order, essentially. And then you will get, yes, that definitely works. So you take the partial order, so here A is less than AB, BC is all on its own, and then you take the clique complex of the partial order of the edges by inclusion, and that'll give you the same structure as what I just described here. So what does this capture? Well, one thing that it doesn't capture is intersection structure. So exactly the thing that I wanted to capture on the prior slide of all these intersections among the hyperedges is absolutely not captured in this barycentric subdivision unless the intersection is present as a hyperedge. So in this case, B here is the intersection between A, B, and B, C, but it's not present as a hyperedge, and so there's nothing to tie those two pieces of the barycentric subdivision together. And so claim, which I have proof up here for but haven't written down yet, is that the zero-dimensional homology of this restricted barycentric subdivision, the dimension, or the 0th Betti number, is bounded above by the number of what we call toplexes of the hypergraph. So a toplex is a hyperedge that is not contained within any other hyperedge. So here A, B, and B, C are toplexes, but A is not a toplex. So the number of components of your resulting simplicial complex is bounded above by the number of toplexes, and this is sharp if there are no hyperedges contained within a pairwise toplex intersection. So the picture here is a proof by picture. So each toplex is going to be above, in our partial order, all of the things that are contained within it. And only if there's a vertex, or sorry, a hyperedge that's contained within two toplexes do we merge two components. And so this is the proof by picture for this particular claim. So this notion of homology, or this topological structure, captures toplexes, whereas the simplicial complex one doesn't have anything to do with toplexes. So moving on to another notion here, again using the barycentric subdivision, but going a little bit different route with it. Here we do need the barycentric subdivision of the full closure of the hypergraph. And now we're going to quotient out by a subcomplex induced by missing hyperedges. So here the missing hyperedges are B and C, and this is the subcomplex because they're not connected directly, they have to go through BC. And we quotient out by this space by this one. Intuitively, this is what we're going to be computing the homology over. Of course, we're not actually building this space, we're doing a quotient of the homologies, but you can intuitively think about it like you're taking the homology of this cell complex here. Here we have the intersections are kind of preserved in a way through the quotient structure, but actually I probably should strike through this because you always end up getting one component in your quotient because everything that's not in your hypergraph collapses down to a single vertex and is connected to all of the components. So you're not really preserving the quotient structure, sorry, the intersection structure, just a little bit. And then the open question is, how do loops form? What do loops mean? I mean, we can see how they form, but what do they mean? What are they counting or finding in the hypergraph? So one kind of idea that I had about what one-dimensional cycles are finding is that it's related to the existence of independent paths between missing edges among existing edges. Why do we care about this? I'm not really sure, but maybe we can characterize these one-dimensional cycles using this notion. So in this case, what I mean by that is the missing edge B and the missing edge C are connected through the edge BC, which we see through this cycle here. And then in this hypergraph that has two components, notice the components get merged in this relative barycentric subdivision. And we see that, again, the path from B to C and the path from D to E are shown in cycles here. But if you start to get more complicated, this is the example that I was showing previously. The red on this simplicial complex barycentric subdivision here are showing the subcomplex induced by the missing hyperedges, and when we quotient it out we get something like this. And notice that while there is a path between this red vertex, which is corresponding to this hyperedge, and this one corresponding to this missing hyperedge, it goes through something that's not a homological cycle, and so it's not going to become a cycle in the quotient. However, these two kind of paths between missing edges do show up as cycles. So then I'm adding that are on homological cycles, question mark. So clearly there's work to be done here to figure out what is this one-dimensional structure really showing from the hypergraph. Okay, so I'm going to pivot then to the third. So this half of the talk has a number of open questions if you're not getting that yet, but that's where we are with this work right now. So pivot to somebody else's work. Bressan, Lee, Ren, and Wu in 2019 published this paper called The Embedded Homology of Hypergraphs and Applications. It's very related to the path homology, if you're familiar with the path homology. They build a chain complex from a hypergraph, not a simplicial complex, but a chain complex. And I'll show you how they do that. So the ingredients that you need are first the chain complex from the closure of the hypergraph. So here our chain complex from the closure has A, B, and B, C in C1 and A, B, and C in C0. And these are our boundary maps. And then we take a graded subgroup of that chain complex that comes from the hypergraph. So we only put things that are hyperedges into our graded subgroup. So here A, B, and B, C are there, but now in the 0th piece of the graded subgroup, we only have A. Okay, so we have the chain complex here, we have the graded subgroup, and then we form what they call this infimum chain complex, where it's a subgroup of D such that the boundary maps from C, from the original chain complex, can be followed. So here we take the infimum at dimension I is taking D sub I, so this dimension I graded piece from the hypergraph, intersecting that with the pre-image under the ith boundary map of the di minus 1. So basically, the intuition is at dimension I, we keep only those groups of hyperedges whose immediate boundary is also present. So in the case of this hypergraph up here, the one-dimensional, there's nothing because the only boundary is, well, the only thing in dimension 0 is A, and that's not the boundary of any edge. There's also no cycles here, which would have 0 boundary and thus would be remaining. But in dimension 0, because the pre-image of the 0 boundary map is everything, we get everything in the 0th dimension. Just an intuition check. When I first was looking at this, I was thinking to myself, okay, so it's you keep all the hyperedges whose immediate boundary is present, but it's not all the hyperedges, you keep all of the groups of hyperedges. So in this case, A, B, and B, C, the boundary of each of those is not present, but the boundary of the sum of A, B, and B, C is present as A plus C in the 0-dimensional space from the hypergraph. And so you would keep AB plus BC in the infimum group for dimension 1. So that's just a little catch in my intuition, at least, and maybe in yours as well. So then the embedded homology of the hypergraph is the homology of this infimum chain complex. So we take our kernel mod image and we see in this case the only interesting homology is here at dimension 0. Okay, so one more intuition to get you thinking about what this might be capturing in the hypergraph is the notion that I am calling uniform cycles. So in dimension 1, a uniform cycle is a graph cycle, basically. It's a cycle in the hypergraph where all of the edges are size 2. Versus this one over here, which is a cycle in the hypergraph you could think of, but this edge up here is size 3, not size 2, so it's not a uniform cycle. All the edges are not all the same size. And so in the case on the left, the infimum of dimension 1, of course, we take D1, which is generated by all 4 edges, intersect with the pre-image of the D0, and D0, of course, there's nothing there, but the pre-image contains AB plus BC plus CD plus AC, imagining that these are all A, B, C, and D. And so there is something in that infimum complex at dimension 1, whereas over on the right, the only thing in D1, we're missing we're missing BC in our D1, and so when we take the pre-image by the boundary map, we don't get anything because AB plus BC plus CD plus AC is not in D1, and so we don't preserve this non-uniform cycle. So in higher dimensions, we can't just chain edges forming a cycle of edges of size 3 forming a cycle that we would think of, like if all of these had size 3 instead of size 2, that does not make a uniform cycle because it's a uniform cycle in the kind of the graph sense, but not in the homology sense. So you need the voids in higher dimensions, so bounded by uniform sized edges. Okay, so that's what one of the things that embedded homology is kind of preserving or capturing. So let me summarize these four notions before continuing with the last bit of the talk. So here are, what I want to show here is the differences and similarities from all of these different notions of homology. So let's have three very simple hypergraphs, just moving around where here we have only toplexes, and here we've added a singleton vertex, and now we've moved that singleton vertex down here. So these are the dimension 0 and 1, the homology groups of those four notions. What I wanted to point out here is, of course, the simplicial complex homology is the same in all three cases because the closure is the same simplicial complex. The barycentric subdivision homology is the same for the first two, whereas the relative homology and the embedded homology are the same for the second two. So we can't really use these as an invariant. They can't all tell the difference between these hypergraphs. I'm sure there's a hypergraph somewhere that has all of the notions being the same. But if you start looking at the generators of homology, you can start to see some differences. So here, where these two have the same homology groups, the generators are of different lengths, you would say, and so that can distinguish them. Okay, so in the last 10 or so minutes, I'm going to skip some notions. I'll just give you a little advertisement that we also have been looking at kernel, image, and co-kernel homology. So if you take a chain complex from the simplicial complex and a chain complex from the infimum, and you look at mapping between the infimum complex and the chain complex of the closure, you can kind of measure the difference between those two things by looking at the kernel, image, and co-kernel of that map. But the punchline being that it's not always different. So the homology of the infimum complex might actually be isomorphic to the homology of the simplicial complex, even though the structures, if you look at them, are very, very different. And so trying to understand what that kernel, image, and co-kernel might be telling us. I do have a couple of slides on that if anybody's interested in any of those details, but I want to talk briefly before I conclude about other finite topological spaces. So things that are not simplicial complexes, not chain complexes, but other topological spaces that we can build. So here's another example hypergraph, and I'll tell you about two topological spaces that we can build that are based on this structure here. So the first is we take the set of hyperedges as the subbase for a topological space. So here's a set of hyperedges. If we take all of the multi-way intersections, which of course is possible because we've got a finite set of sets, take all the multi-way intersections to get a base of a topology, and then we take all of the unions that of the elements in the base. This forms a topology on the underlying set of vertices of the hypergraph. Okay, very, very cool. We can also form a partial order of the edges. I mentioned the partial order earlier when we created the barycentric subdivision. So form a partial order of edges using set containment as the ordering criteria. And then you can use that, that partial order to form a topology using the Alexandrov construction, which is by taking the set of principal filters, upsets, or you can also take the ideals, either way. I did it in my example as filters, the upsets. So the open sets in your topology are all of the filters in the post set. So in this case, here is my post set of edges. The principal upsets are AB with ABCD, that edge, those two edges here, AC and ABCD, and then the going up from C, and then also ABCD on its own is an upset. And then if you take all the unions of those, you get all of the filters, and this is the open sets of that topology. So one might ask how the singular homology of these topological spaces relates to the simplicial homology of the other things that we've been talking about. And that also an open question that I'm very interested in pursuing. It may well be easy. I know there's some work from McCord on finite topological spaces and singular homology of finite topological spaces that I need to dive into and see if the answer is already out there, perhaps. And just a note about duality and topology. So I mentioned duality earlier when we were talking about the nerve and the closure, the relationship between those two. So again, hypergraphs come in dual pairs. Here's the hypergraph that I had on the prior slide, but now colorized. And here's its dual, where the vertices are colored by the edge that they came from in the forward, the original hypergraph. Of course, the two topological spaces that I described on the prior slide can be constructed from this dual hypergraph. And so now you're thinking, great, now we have 4 topologies that I can build. But it turns out that they actually come in dual pairs. So the topology that's formed by the filters in the edge partial order is the same topology as the one formed using the edges as the subbase in the dual. So if I take the partial order of the edges here and I form my upsets, and I get a topology here, if I take my edges as the subbase of my topology and I form a topology, I get the same topology. So there's really only 2 of these. Here's a proof by example if you really are interested to see that these are in fact identical, and the proof goes beyond just example. We know it for real. Okay, so how does homology play with duality? So remember that Dowker's theorem implies that the homology in the simplicial complex is the same as the homology of the simplicial complex of the dual hypergraph. And then the question might be, if I take the hypergraph and I take its dual and I do some of these other constructions, other topological constructions, does duality preserve homology in these other notions? And the answer is an emphatic no. There's a very simple counterexample. In fact, this example that I've been using throughout is a counterexample in all cases. Here we see that the restricted barycentric subdivision here has 3 components, and then the dual has 4, so that's out right away. The relative barycentric subdivision here has 2 loops. Here it has 4 loops. We're done. And same in the infimum chain complex, we see that they are in fact different in the two cases. So another open question is, can we define a notion maybe of an approximate isomorphism? Can we find something that traces through the duality to relate the structure of the forward to the structure of the dual using these other topological notions? And maybe not. Maybe the simplicial complex is really the one that's capturing vertices and hyperedges simultaneously, and the others are only capturing properties of vertices or properties of edges. Not necessarily not necessarily a judgment on these other notions, just an observation to be aware of. And so just to summarize what I've talked about here with the topological characterization of hypergraphs, we had this very simple interpretation, which is taking the hypergraph closure, the simplicial complex, which has its place. It captures the intersection structure of the hyperedges. But to get more complex, to try to not add information, we wanted to understand what other hypergraph properties we wanted to capture, and came up with these other notions: the restricted and relative barycentric subdivisions, the embedded homology, and then what I alluded to, the kernel, image, and co-kernel homology, and then these other finite topological spaces. And in terms of applications, this notion that I have on here of holes as hypotheses is something that has gained traction with some of the folks that we've worked with, trying to think about where, let's say you have a hypergraph from a protein interaction network, for example. What's missing in that, this is built up from tons and tons of experimental data, right? And so they can't do all the experiments. So what's missing, what's in voids in these hypergraphs might be opportunity for more research. Maybe we want to tell the biologist, you should check and see if these 5 proteins actually interact in a full way, because we see that pairwise or 3-way or whatever, they all kind of are interacting. So maybe there's an opportunity for some new experimentation to go on there. As I mentioned, a lot of this in the second half was ongoing work, extending to things like persistent homology. What I talked about in the second half was pretty much restricted to just homology on its own, not persistent. So can we add functions or distances to induce filtrations? the embedded homology work by Bresson et al. Does have a notion of persistent homology associated to it, as well as stability. It's a recent paper on the archive and maybe published, I'm not sure, on stability for that embedded homology, which is very interesting. And then there's plenty of other open questions. I welcome any open questions from you all. And this has been fun work, and we hope to put together a paper at some point here that kind of summarizes topological notions of hypergraphs and what we know and what we care to know. So I will close it there. Thank you.
Thanks very much. Let's thank Emilie. And we will open the floor up for questions.
Adam, I see you have a question. Good to see you.
Yeah, it's good to see you. Thank you for the talk.
Yep.
I have two questions. The first one was when you were talking about the relative homology.
Yep.
So if we take the closure of the hypergraph, we get a simplicial complex.
Yep.
And we can look at which simplices we needed to add in order to close it up.
Yep.
And so if I have that picture of a simplicial complex with like some highlighted simplices representing what I needed to add, is that enough information to fully recover the hypergraph?
Yeah, it should be, because you just have to remove those lit up simplices and you'll have the hypergraph back.
Okay. And so then my second question, which might not be surprising, is I'm curious if anybody's thought about like defining a sheaf on the closure of the hypergraph and then taking the sheaf cohomology. Because I could define a sheaf where each simplex either gets sent to a one-dimensional vector space or zero, depending on if it was already in the hypergraph or not. And so it's supported on some subset of the simplex.
Right.
And then I just take the sheaf cohomology of that sheaf.
I don't know if anybody's thought about that, but it certainly is an interesting idea to try. So if you had one-dimensional vector spaces, I'm trying to think about the restriction maps.
Yeah, I think you could set it up so that it's all just identities or zero.
Yeah, right.
And then I think, I mean, you should get something that is related to either like Borel-Moore homology or compactly supported cohomology or something like that.
No, I certainly haven't thought about it, but it's an interesting thought. Is anything going to be messed up because you can have a hyperedge that's there and then a subset of it that's not there and then a subset of that is there, and you can kind of chain between existence and non-existence of edges in an order relation?
Yeah, that would be a problem. Yeah, that's the issue. Yeah, because you need restrictions to commute.
Yeah. So I think there might be a way of fixing, getting around that, but that's, I think, where you'd get some issues.
Interesting. Cool. No, thanks.
Thanks for the question. Michael, I see your hand up.
Yeah, I had a question. So some time ago, I was trying to look at hypergraphs for market basket analysis and see if, you could tell the difference between different types of customers. The only thing I could think of to do was to just take the simplicial complex. It's the closure of everything.
Right.
I'm wondering if any of your other methods might tell you something different.
Yeah, potentially. So there's the simple kind of combinatorial, not necessarily simple, but there's the combinatorial methods where you can look at kind of the neighborhood of particular vertices. If you're wanting to tell the difference between Tom and Mary and their behavior in the hypergraph, you can look at some local notions, either combinatorial or perhaps even building some sort of notion of a local homology or relative homology local in the hypergraph. So I think the moral of the story here with this topology is that the simplicial complex sweeps a lot under the rug, or rather puts a lot on top of the rug, because you're adding a whole bunch of simplices that aren't necessarily there. So you're ascribing behavior to a particular vertex that may not actually be present. And so if you think about the hypergraph without adding that structure in some way, you'll be able to separate things more with these other notions. But it's not obvious necessarily which one to pick or which ones to pick, or maybe there's something else that we haven't thought of yet that could capture some other structural notion, either local or global.
Okay, thanks.
Mm-hmm. Any other questions?
If not, then let's thank Emilie again.
Thank you.